Awesome. So we're very happy to have Rich Townsend here today to talk to us about some work that builds on MESA, multidimensional stellar grids. And anyone who uses MESA probably knows Rich's name. If you're like me and you want to run it really quick, you go to the MESA web, which Rich's group generously hosts as well. It's an awesome tool, especially for education. So we're very happy to have Rich here today. If you have questions, drop them in the chat. We only have one talk today, so we have plenty of time for discussion after Rich's presentation. So Rich, I'll turn it over to you.
Okay, thank you very much for that nice introduction, Michael. Let's share my screen. Yeah, so is that showing up okay?
Yep, looks great.
Okay, great. And I'm actually just going to put my headset on because I have some laundry running in the background and I don't want that to disrupt. Doesn't seem as though that's working, so I'll carry on talking like this. Can you still hear me now?
Yep, we hear you just fine.
Okay.
We don't hear laundry either, so.
Okay, that's great. Okay, so what I'm going to talk about today is a project that started actually as an add-on to MESA, but now it's kind of a standalone thing. And it's one of those, it's the sort of project where there's nothing that revolutionary in it, but it kind of scratches an itch that just persists over a long time. It's sort of a project born of frustration that nobody has actually made an open source package for doing what MSG does. And I eventually couldn't stand the itch anymore and I had to scratch it. We ended up with MSG. So it stands for multidimensional. I've written it as stellar grids, but it really should be spectral grids because it's really about grids of stellar spectra. It started out as Madison spectral grids, but then I realized if I got fired for gross incompetence, the name would stick with me and that wouldn't be good. So I just made it institution neutral. So the context really for MSG is a problem that is often encountered in stellar astrophysics. We've got some model of a star system, and at some point we've got to calculate an observed flux spectrum. The way we do that is we integrate the specific intensity, I lambda, over the visible disk of the star. I hope my mouse pointer is showing up. So the observed flux here on Earth is a dilution factor, the ratio of the stellar radius squared over the distance squared, times this two-dimensional integral over the visible hemisphere of the star of the specific intensity with some weighting factors. And the specific intensity depends on wavelength, the angle between the line of sight and the local surface normal, and the local photospheric parameters, which I've written sort of generically as a vector x, and that vector may have components comprising the effective temperature, the surface gravity, the metallicity, maybe some microturbulent stuff, maybe some alpha enhancement. So for boring stars, which is most stars people are interested in, this sort of vector of photospheric parameters, x, is independent of position on the surface. All of the surface has the same effective temperature, the same surface gravity, the same metallicity, and so on. And that means that we can do our integration over angle, kind of over the phi angle, we can do that analytically, and then over the theta angle, we can kind of pre-compute what the angular integral over theta of the specific intensity is. And we end up with an expression saying that the observed flux here on Earth is just the emitted flux at the stellar surface times a dilution factor. And I'm pretty sure I've dropped a factor of 2 pi here, but who cares? So that's boring stars. For interesting stars, the photospheric parameters can depend on where you are on the stellar surface. This might be due to temperature spots. It might be due to abundance inhomogeneities. Also, if the star's rotating and there are Doppler shifts, those Doppler shifts will depend on where you are on the surface. And so we have to do the full disk integration. But either way, in order to construct a spectrum for either a boring star or an interesting star, we're going to need a flux spectrum at the stellar surface, F lambda, or a full intensity spectrum at the stellar surface, I lambda. And so the question we're addressing here is, how do we actually calculate I lambda and or F lambda? And these are really outputs of the stellar atmospheres problem. And to calculate them, we have to solve the radiative transfer equation for a model atmosphere that has a given set of photospheric parameters. And this can be done using a variety of existing tools like Atlas or T-Lusty or Phoenix. But this is a time-consuming process. It can take anything from seconds to days to do this sort of calculation. And it's technically challenging. You need to wrangle a lot of atomic data with level energies, then line lists. You maybe have to worry about non-LTE effects if you're dealing with O and B stars, or if you're dealing with, let's say, red giants with very dilute atmospheres. And then at lower temperatures, there's molecules to throw into the mix. So it's kind of a daunting task to do the calculation yourself. So maybe you want to rely on a published grid of spectra where a paper has come out introducing a new data product, a grid of synthetic flux or intensity spectra over some sort of mesh of different X values. But the problem with this is you're restricted to considering stars that have photospheric parameters exactly at the nodes of the grid. And the data files for these grids tend to be in bespoke and rather random formats, often ASCII or FITS tables, and they can run into the sort of hundreds of gigabytes in size. It's not the sort of thing you can easily access. So this is where multidimensional spectral grids comes in. So this is a software library that facilitates interpolating within a pre-existing grid of stellar spectra. It doesn't actually calculate the spectra for you. You've got to get those from somewhere else, get them into MSG's sort of internal format, but then MSG makes things very straightforward for you to calculate a spectrum for any combination of photospheric parameters that lies within the outer boundaries of the grid. And you can do this from Fortran, Python, and C, which I think are probably the three most favored languages in astrophysics. The actual interpolation is done by cubic tensor product interpolation, and I've got a few slides coming up that kind of go over that, because it was something I'd never heard of, and then I kind of figured out an approach for doing interpolation in an arbitrary number of dimensions, and then I dug around online and found it had a name, which is cubic tensor product interpolation. So MSG stores all of its data on disk in HDF5 files, and some of these files can run into the low hundreds of gigabytes for really, really large grids. But MSG implements a sort of load on demand philosophy, data only loaded when they're needed. And there's a set of controls that you can use to set an upper limit on how many or how much data is stored in memory at any one time, meaning that even with a very, very large grid, you can run on a relatively small memory machine, albeit with a performance impact as data are evicted from the cache and fresh data loaded from disk. So MSG can interpolate an intensity spectrum. So this is an angle-dependent quantity, the angle between the surface normal and the line of sight, or it can interpolate flux spectra, and it can convolve either of these on the fly with photometric response functions to give you colors in various different photometric systems. So next few slides are sort of pedagogical in nature, really because there isn't much in the way of literature, existing literature, especially within astrophysics, about how one goes about doing multidimensional cubic interpolation. I think numerical recipes goes over 1D linear and maybe 1D cubic and maybe considers 2D cubic, but they kind of go down a rabbit hole of cubic splines, which have advantages, but also disadvantages. So what I'm going to do is just really present a pathway that leads us up to cubic tensor or cubic tensor product interpolation, so you can get the gist of how it works. So firstly, for linear interpolation in 1D, suppose we have an input grid of abscissa values, x1, x2, all the way up to x however many, and corresponding ordinate values, f1, f2, and so on. Suppose we want to interpolate the value of f at some x value that lies between xi and xi plus 1. Here's a formula we can use. It's basically just a weighted sum of the function values at the I and I plus 1 grid points. The weighting functions themselves are these linear basis functions, and they depend on u, which is a sort of weight function that says how far across the interval from xi to xi plus 1 we are. So if x equals xi, u is 0. If x equals xi plus 1, u is 1. And so this linear interpolant goes smoothly and linearly from fi when x equals xi through to fi plus 1 when x equals xi plus 1. So this is all, really basic stuff here. So to go from linear to cubic, there are a number of different ways you can do it. This is the cubic meet approach, which is where we can write the interpolant as a sum of 4 terms. So they are the function value at either ends of the subinterval, and the first derivatives of the function values evaluated at either end of the interval. And then we now have a set of 4 basis functions, C1 through 4, which are the cubic basis functions. And the advantage of going from linear to cubic is that not only is the interpolant continuous at the subinterval boundaries, but its first derivative is also continuous. So again, this is not really anything new to probably all of you, but I just want to lay this out there as some sort of foundational work. So to go from 1D to 2D, things start getting a little bit more interesting. A bilinear interpolant in parameters x and y can be written as the sum of 4 different terms, and those terms are it's basically a weighted sum of the function values at the corners of the sort of box you're interpolating in, and we can write it in a relatively compact form, a coefficient matrix times the product of a pair of the linear basis functions. So the matrix has 4 values, being the function values at the corners of the box we're interpolating in. And in fact, we can generalize this up to the cubic case using the expression at the bottom. And again, we've got a rank 2 sort of matrix or tensor of coefficients times a product of 2 of the cubic basis functions. And the coefficients, there are now 16 coefficients comprising the function values at the corner of the square we're interpolating in, or rectangle, the first derivatives with respect to x and y, and then the cross derivatives, partial with respect to x and y. So we need 16 values to do this interpolation. And the cubic function is continuous and continuous in its first derivatives at the corners of the rectangle we're interpolating in. Okay, so going from sort of 1D to 2D can be generalized from going from sort of 2D up to any number of dimensions if we just generalize these formula. The expression I give here is the generalization of the cubic formula. We have some function of n different parameters. So we're interpolating in n dimensions, and we can write the interpolant in this form. It's basically a tensor of rank n, then inner producted with this term here, which is essentially another tensor of rank n that is formed by products between the different cubic basis function. So in n dimensions, our coefficient tensor has 4 to the n elements, and it's those elements are basically the function and the partial derivative values at the vertices of the n cube, or the tesseract or whatever we're interpolating in. So this expression looks kind of daunting, but when you actually get down to implementing it in code, there's sort of a lot of regularities that you can take advantage of. Fortran, which the library is written in, doesn't have direct support for variable rank arrays, but I get around that by storing everything in one-dimensional arrays and then doing a lot of index arithmetic on the fly. Okay, so as I just mentioned, the architecture of the MSG library the sort of core functionality is written in Fortran, and it can be accessed from Fortran, but I provide a set of higher level APIs that are sort of recommended for the user to interact with the library via. The Fortran API is written in Fortran, callable from Fortran, and it just interfaces directly with the core library. The C API, surprisingly, is also written in Fortran. So all of the routines in the C API are directly callable from C and appear to external programs as a C library via the ISO-C binding interoperability functionality in relatively recent Fortran standards, I think maybe 2003 onwards. So the C API looks to everything else to be C, but it's actually written in Fortran. And so it's that API that the Python API accesses. The Python API is written in Python, can be called from Python. So the Python calls the Fortran thinking it's talking to C, and the Fortran listens to the Python thinking it's talking to C, but in fact, each of them is talking directly to the other. So user code can access MSG either through Fortran, through the C API, or through the Python API. And the examples I'm going to show you in a moment sort of showcase a few applications of the Python API to highlight how the interface is relatively straightforward to use. It's kind of object-oriented, so it's not too difficult to get your head around. So this first example is calculating just observed flux spectra for Arcturus and Vega. So in the code on the left-hand side, and this code isn't complete, you know, I've left out import statements and things like that. But it should be enough to give you an idea. In the first line of code, we load a object, a spec grid object, which is basically an in-memory representation of a grid. It's an object you can interact with to do interpolations. So we load one from a disk file called sgcap18 course.h5. This is an HDF5 file. And this contains one of the grids published by Carlos Allende Prieto in his 2018 paper. So that single line sort of prepares the grid for interpolation, but it doesn't actually load any of the data off disk. It loads some metadata, but you know, that's pretty lightweight. It's not loading you know, hundreds of megabytes or gigabytes of data off disk. The next few lines of code set up stellar and photospheric parameters for Vega and Arcturus. So X is actually a Python dict that stores photospheric parameters, so effective temperature, log gravity, and the ion abundance. Then we've got a distance and a radius for each star. And then down at the bottom, we set up a wavelength abscissor and then calculate the observed flux of Vega and Arcturus by basically just diluting the surface flux of the two stars given the vector photospheric parameters and the wavelength abscissor. And then this plot on the right shows what the spectra look like. And you can see Vega's a nice blue star, and Arcturus is definitely a much lower effective temperature red star. Okay, so the next example shows us how to, or demonstrates how one goes about calculating things like isochrones or quantities in a color magnitude diagram. So as well as spec grid objects that represent a grid of stellar spectra, MSG offers things called PHOT grids, which are photometric grids. And these can either be created by loading a spec grid and telling it to convolve on the fly with photometric pass bands, or you can sort of pre-bake a PHOT grid to avoid any of the overhead of the on-the-fly convolution. So in this snippet of code, I've got two FOT grids, one corresponding to Johnson B band and one to Johnson V band. And I loop over all the points in a set of isochrones. These isochrones are actually taken from the 2016 MIST paper, MESA Isochrones and Stellar Tracks. So I loop over a set of points in an evolutionary track. I set my photospheric parameters based on data from the track. And then I use a try except exception handling clause to make sure that if I try to interpolate at a temperature or a gravity that's outside my grid, I just set the fluxes to not a number values rather than crashing. So the nice thing about the Python interface is it actually has exception handling that allows you to deal with cases where points fall off the grid. And here I've just set values to nans, but in a more sophisticated treatment, I could imagine, extrapolating from grid boundaries. And then the final bit of code just converts observed fluxes into B bands and V band absolute magnitudes. And the fluxes returned by MSG have the 0-point correction built in. So you don't need to add on any additional constant term to the magnitudes to get them in the right place. And so here are the isochrones for a range of different cluster ages. And so you can see, obviously the young stars all lie near the main sequence. And as we go to older ages, most of the stuff is evolved off the main sequence. Okay, I think this is my final example. This is a demonstration of calculating light curves for a slowly pulsating B star. And this is actually using the formalism that I describe in my 2003 paper as a reference at the bottom there. So this is an example of how you can use not just intensity data from spectroscopic and photometric grids, but also things like moments of the intensity data. So the D moment functions I'm calling here are actually the Legendre moments of the surface radiation field. And MSG can give you that. It can also give you things like the Eddington flux and the mean radiation intensity and the radiative K tensor and things like that. So it can give you a little bit more than just a plain flux or a plain intensity. So what I do here is basically calculate the intensity moments, not only the intensity moments, but also their derivatives with respect to effective temperature and gravity. And I can do that because I'm doing cubic interpolation. I can also interpolate derivatives for free that are completely consistent at every point with the actual interpolants. I'm not going to go into any of this math in detail. It really just comes out of my 2003 paper. But this is how easy it is if one is given the amplitude of radial perturbations and temperature perturbations and gravity perturbations at the surface of the star. You can then go straight away and calculate a light curve in various different photometric filters. I should add that the amplitude of the radius, temperature, and gravity perturbations at the stellar surface are exactly the sort of things that are output by my Gyre oscillation code, which also works with MESA. So a bit of a shameless plug there, but this is really to demonstrate how one would take output from Gyre and synthesize light curves. And it really can be done with a few lines of Python code and some calls to MSG. Okay, so I've no idea what the time is or whether I'm running. Oh, I guess I've run over just maybe a tiny bit. That's great. If you want to find MSG online, the code sits on GitHub, and there's a documentation site on Read the Docs. And I'm probably more pleased with the documentation than I am with MSG itself, because I think writing good documentation is hard work, but it can be really rewarding if you end up with, high quality product. And I'm especially pleased at how this turned out. So that's where you get the code and the docs. However, to use MSG, you'll also need grid files, and they're stored separately from the GitHub repository, because these grid files are huge, but they're also changing as I fix mistakes and add new data and things like that. So I have a separate website that hosts a number of different published grids, so grids from the literature that I've converted into MSG's format and then sort of packaged up. And as part of the code distribution with MSG, I also provide a suite of tools that allows you to ingest data in a variety of formats into MSG's format. And I'm always on the lookout for new grids, especially intensity spectra grids rather than just flux spectra. And happy to help anybody who has a grid get it into MSG's format and then host it on my website. And with that, I think that's all I have. So thank you.
Wonderful. Thank you, Rich. That was very nice. We have time for questions. As we noted at the top, we don't have a second speaker today. So we'll take questions for like 10 minutes or so. And then before I do that, I will encourage all of you who are on here, especially those who have not given a seminar, to show off your cool software stuff by raising an issue on the vast GitHub page saying that you want to give a talk, because we are looking for speakers for the remainder of the year. So if we have questions for Rich, can you drop them in the chat or raise your hand or just start talking? I have too many screens open. So Rich, I'm not familiar with how these grids are produced in the first place, and I know that's not what your code does, but what sort of codes are used by the different groups to make the grids that you then interface with?
So there are some open source tools like Bob Karutz's Atlas and Synthy.
Okay.
And as well as those tools, there are just grids that he's made using those tools. And my understanding is that getting Atlas to work is a real pain in the neck.
I see.
I think parts of it are written in Fortran 4 or Fortran 66. So
yeah, that's always.
But there are also there's another set of codes that I've actually used myself called Telusty and Synspec, written by Ivan Humany and Thierry Lanz.
Sure.
And they're a lot easier than Atlas to use, although they still have their sort of downsides. And really, the procedure one uses to generate one of these grids is really, I guess, writing some sort of Python or scripted framework that will run Telusty and Synspec over a wide range of parameters and spit out a spectrum. So, you know, it's really just a very boring standardized grid calculation. It's very easy to parallelize, but it can be quite time consuming. So parallelizing it is a must. But as you get more and more ambitious in the number of different photospheric parameters you want to explore by your grid, you start running more and more into the strange parts of parameter space where your codes crash.
Yeah.
And you start getting voids and ragged edges, and the need for human intervention goes up, or you need some way of dealing with voids in your grids where your code just couldn't calculate a solution. And MSG sort of partly handles that. It allows for grids with ragged boundaries. It allows for grids with holes in them. At a future point, I'd like it to be able to interpolate over any holes. But for now, it just returns an exception that, okay, you've tried to interpolate in a hole.
I see.
So I've tried very hard to stay as far away from actually generating the grids as possible, because, you know, that is really just a whole lifetime you can sink into that. But I haven't been entirely successful, and so a few of the grids on my webpage were actually generated by me.
Okay. We have some more questions. Sam asks, is it Fortran 77 or 90 or something later?
I think it's probably Fortran 2008.
Okay.
So I try to keep things as up to date with a standard as I can, but also recognizing that the number of compilers that support more recent Fortran standards completely is pretty small. So in fact, it was supporting use of modern Fortran stuff that led me to develop the SDK that ended up the MESA SDK. So, that's another project that, sort of grew out of my involvement in MESA, but then fed into my stuff like MSG.
Okay. And along the same lines, how are the integrals actually performed? I guess, Sam, you're asking what sort of quadrature?
So for the disk integrals, that the ones that I showed you at the beginning, those are not things that MSG has any views on how to do, because they are part of the disk integration process that comes after you've found a way to synthesize a spectrum at each point on the stellar surface. So in practice, what people will often do is divide the stellar surface up into a number of points, maybe equidistant in projection onto the sky, or maybe equidistant in theta and phi, or maybe they might triangulate the surface and have a load of surface elements, and then calculate individual spectra for each little fragment. So in practice, that quadrature is really done probably not as it's not done using any sophisticated kind of quadrature. It's just, let's throw a set of points on the stellar surface and add up the intensity from all of them. Now double the number of points. Has the result changed? No, we're good.
Cool. Let's see. There was a question about where the source is hosted, Alex, but Alice posted the GitHub link to that.
Okay.
That should handle that. From Andrew, can you give an idea of the computational cost for just the spectral grid interpolation given a few gigabytes of RAM?
It depends how many dimensions you are really interpolating in. So when I say dimensions, I mean photospheric parameters. Yeah. So for a 2D grid, which is just temperature and gravity, and interpolating at 1,000 wavelength points, I think the cost is milliseconds or smaller. As once you start going to finer wavelength grids, I mean, basically the cost grows linearly with the number of wavelength points you want to interpolate, and it goes as I think 2 to the power of n, well, maybe 4 to the power of n, where n is the number of dimensions in the grid. There are some demonstrations on the documentation site about how things slow down once caching kicks in. But for a few gigabytes of memory, unless you're calculating very, very high resolution spectra over a long wavelength interval, I think it would be unlikely that you would fill the cache, assuming the cache was set to a few gigs, the cache limit.
Along those lines, is there a maximum dimensionality? I guess that would depend on what the input data has done, but what's,
there is no maximum dimensionality modulo the fact that I mean, if we had a 100-dimensional grid, I think things would go pretty slowly. Once the cache you're more likely to run out of cache once you go to higher dimensions, because you need more data points to interpolate within a single cell. But if memory is no constraint, then there really is no limit on the number of dimensions you can go to. Absolutely none. 1,000-dimensional grid, sure. Because everything is packaged down to one-dimensional arrays. And I've been quite careful in thinking about, storage layout in memory and things like that.
Very cool. Let's see. Another question from Alex. And is it possible to model an atmosphere using MSG and some thermodynamic plus composition by using atmosphere data? Alex, maybe you want to unmute and describe what you have in mind a little bit more. Or not. So I mean, maybe one interpretation of this is to not use the data that you have, but to have just use it as the interpolation interface to something that maybe is a continuous function. I'm not sure.
Yeah, I'm looking at the comment now as well. MSG at its the interpolation in MSG is kind of very agnostic about the sort of data it's interpolating. And at the sort of low level, it's not even aware of anything like spectra or things like that. It's got a basic n-dimensional cubic interpolation sort of core that, in principle, you could rip out and use for interpolating any other sort of data.
Right.
There's a clarification from Alexander.
Oh.
He says, I wonder if it's possible to combine the interpolation scheme and MSG to produce an atmosphere that can be used for reactive calculations.
I'm still not quite sure what you're meaning, Alex. I don't know what reactive calculations are. But one thing I should add is that MSG has no conception of the structure of a stellar atmosphere. The fact that the temperature declines with height, usually there might be some compositional gradient, and it might be, the atmosphere might be out of hydrostatic equilibrium if you're dealing with a wind. MSG has no concept of atmospheric structure. All it knows about is the radiation field emerging at the top of the atmosphere. So the atmosphere structure has kind of already been considered and worked with during the spectral synthesis process, solving the radiative transfer equation. And that atmosphere never actually gets as far as MSG. It's put aside because all MSG cares about is the spectra.
Yeah, I think he understands now. He's clarified. I think we're good on questions. I think we've had a good time, and we've had a fantastic presentation from Rich. Do check out Rich's other tools. I forgot, of course, to mention the Mesa software development kit, which everyone knows and loves, and would cry if it weren't available. So we all do appreciate that work that you have done. And thank you for the great talk. Last reminder, you all have awesome software. Raise a GitHub issue saying I want to present. We're starting to think about the rest of the academic year. Or I guess there's one more month in the normal academic year, but the summer and following. If you would like to present, we're happy to work with you. And I think what we'll do is we'll stop here then.
Okay.